Today is our eighth session, and we will be covering neural networks briefly. But before that, let us revise the previous class. We discussed about random forest. So, can someone briefly, maybe in one or two sentences, explain what you understand by random forest?
Random forest is a ensembling algorithm. It uses the bootstrap and aggregation. So it is a bagging type of algorithm where we are parallelly uh, forming multiple decision trees based on the conditions. And last time we have selected some features like x0, x1, x2, x3. So some pair of features we have selected, and we have created a decision trees for that. That all I got from the previous slide session.
Right. So, what is the benefit of using random forest? Why not? Why this algorithm is used?
To get more accurate prediction.
But decision trees could be
Bigger decision trees are broken into smaller ones.
exactly because it is less complicated and it is a probabilistic model, a stochastic
Coming
model, and it shortens your decision tree. So both these advantages actually render it more relevant in terms of feasibility and usability as compared to long decision trees. So they are adept models used for classification problems. So with this, we move on to neural networks. So, anyone, what do you understand by neural networks? Looking at the diagram that you can see.
Yes, ma'am. This is a deep neural network. No? Where is the input layer, output layer? There is a summation, this summation, and there is a activation function in the output. Every node have two functions. It sums all the inputs, and there is activation function
Hmm.
we have. And there are three hidden layers are there, and this is feed forward network.
Okay, this is a forward network. Okay, fine. So, in any given neural network, you have an input layer, you have the inner intermediate layers, and you have the output layer. On the screen shown here, you can see three layers, but this discontinuity symbol actually symbolizes that you have multiple n number of hidden layers. So you have these many hidden layers inside it, and each node, each this circle is called as a node or neuron, or in general terms, it is also called as a perceptron. This hidden layer neuron, it is guided by all the input layer neurons. Every node will be connected from all the preceding layer neurons, and it will have two components. One is the summation and the other one is the activation function. The summation will comprise of the weighted values of the input features. So for example, this is x1, this is x2, this is x3, this is x4, this is x5, and each of the arrows connected from all of these feature vectors are symbolizing the weights associated with these feature vectors. So basically the summation term expands to summation of wi xi, where wi means the weights for I equals to 1 to I equals to n, and xi symbolizes the feature vectors x1 to xn, right?
yes, ma'am.
Okay. And the other one, this is the function. So this is the activation function, what you are going to use for it. So there are several activation functions that people use. Most popularly, the activation functions which you use are amongst these. And amongst these also, mostly you use sigmoid and ReLU function. So I hope you are aware of these functions.
Just have a quick recap of each of these. Quickly, can you give us
Okay.
the glimpse?
Okay, as symbolized by the equations here, it is already self-explanatory. For example, the activation function, this first one is 1 by 1 plus e power minus z. So where z is your horizontal axis and a is your vertical axis. So basically, any value of z that you take, it will basically have a range in the y-axis. The range will be 0 to 1 here in sigmoid function. Similarly, here in rectified linear unit, what you do is any value less than 0, that is a negative value, you render a y value corresponding to it as 0, and any positive value you keep it as it is. So y equals to x when it is a positive value, when x is negative then y equal to 0. That is what this is. and so on and so forth. Basically, this is tan h function. So tan hyperbolic function of x. This is how the graph looks. So it is asymptotic at -1 and 1. I hope you understand what you mean by asymptotic.
No, ma'am, no idea.
So asymptotic means it is close to or approaching that value, but never touching that value. It is something like tends to infinity. So infinity is something you can never touch. You can only approach. That was just an example. So understand that this line is, as it is proceeding to the positive x direction, it is going closer and closer to 1, but never touching 1. So then it is called an asymptote. Okay, so asymptotic means it is approaching 1. It was zero point 0.9, then it is 0.99, then it is 0.999, and so on and so forth. But it is never exactly equal to 1. That is what this means. At x equals to infinity, tan h is 1. At x equals to minus infinity, tan h is -1.
What about sigmoid, madam? Will it
Sigmoid
equal to 1?
sigmoid function also, it is asymptotic, as you can see in the diagram itself. It is asymptotic, unlike ReLU function. Here it is exactly equal to 0. It is lying on that graph.
Yeah.
It is not approaching them, but here you see that approaching tendency, right?
Then why we need two functions, sigmoid and tan h? Both
These
are
are just,
almost similar, but
yeah,
polarities
these are similar.
different.
These are similar. In fact, softmax function is also similar. It
Similar.
depends, yeah, it depends on which one you choose and which one works best for your model. It is not absolute, but yes, majority of the times people use sigmoid or ReLU. But you can either way. You can go for tan h, leaky ReLU, or softmax. It depends on your model. Everything depends on your
Okay.
data and your model.
Okay, thank you.
Okay, so if that is understood, I hope these formula are self-explanatory. If you substitute the horizontal axis values, you will see that the vertical axis will look similar to the plots that are shown here. So that is what it is. The functions are shown here, and yeah, tan h is probably not shown here. So tan h, if you expand it, it will be
E power x is equal to 1 plus x plus x square plus x cube plus etc.
yes, exactly. So this expansion, does it have any limit, or it goes on and on?
No, it goes on up to infinity.
Yes, exactly. So that is how your tan h also expands. The formula is different, but the expansion pattern is similar. So it is an equation which goes on up till infinity, and if you set a limit on the precision or the tolerance, then you will be able to approximate the value of the tan h function.
Okay.
So with this, we move on to, yeah, different types of neural networks. Again, I'm going to very quickly touch upon what are the types of neural networks: artificial neural networks, convolutional neural networks, and recurrent neural networks. So basically, artificial neural networks is used for text data, right? So, for example, if we were to use, yeah, numeric data as well. So these kinds of things, these kinds of data tabulation, these can be dealt with using these neural networks, simplified neural networks. So if you're dealing with CNN, so they basically are position independent. So they use a shell associated with it, and they scan through your entire image data. Basically, CNN is mostly used for image recognition. So for example, if you have the image of say a number, maybe image of the number 1, so it is characterized by an upper nose, a vertical line, and a horizontal line with a certain arrangement of those lines, right? So maybe you have a collection of 1,000 images in different formats. You have written the number 1. So now you want your machine to understand that this image will recognize this as 1. So there is certain characteristic traits associated with that number. So basically, every layer in your neural network will have a shell which passes through, scans through your entire image, and every time it recognizes those particular pixels wherein you have a certain arrangement of your line. So basically, this makes your model transition independent. For example, you may have an image where your left corner shows the number 1. You have another image where your number 1 is in the center of the image. There may be one in the right side of your image. So different numbers of images that you're feeding, they may have a different spatial positioning of your number 1, right? But essentially, when you scan through it, then a certain arrangement of your pixel, that is not going to change wherever the location may be, right? So that scanning is done in the form of a shell, that matrix that scans through your entire image. That can be a 3 by 3 matrix that runs through your image, and so on and so forth. So I hope you understand what CNN briefly means, how they basically detect the occurrence of some features associated with your image, and how they detect resemblance or similarity associated with your image. Same is the functionality associated with recognizing cat images or dog images or cow, and so on and so forth. There are certain characteristic traits which they resemble, and those are actually grouped as similar classes, such that they can say with a certain amount of confidence index that okay, this is this particular trait or this particular output. Now here RNN, actually we also have backpropagation, because this is mainly used for voice recognition, all these types of data, and basically yeah, sequential data. So when you have a sequence associated with it, then you have a time component associated with it. When you have a time component associated with it, then from previous time stamp you are basically training your model, and again this is a back propagating kind of model. So every time with your previous timestamp, it is comparing and it is again rectifying. So with experience it is learning. So that is the kind of training that you do in case of RNN. So again, this is not spatially independent. So I hope you understand what you mean by RNN.
Ma'am,
Leaky
you just go through it quickly. We are expecting to discuss this in within 5 minutes only, so that there will be a quick recap of these points. And if something is anything other than we can find, then we can go ahead with that like that.
Yes, yes.
So you can go fast, ma'am, than this.
And if any particular point is not understood to you on this screen, then you let me know, so that we will have an elaborate discussion with that.
What do you mean by parameters sharing in ANN and SS for RNN?
Okay, so you have certain feature vectors, parameters associated with it, right?
Okay.
So, parameters of any neural network, any training instance, such as weights or bias, CNNs have the capability of sharing these parameters to a certain extent. And as a result of that, what happens is the training process becomes relatively faster as compared to simpler neural networks like ANN. Why is that so? Because now the number of total instances of the parameters that are to be used are less. So there is less updation of parameters in every training iteration. So what happens is eventually with less number of weights and bias, you are able to train your model completely because of this factor of parameter sharing. That is, however, not applicable in case of simpler networks like artificial neural networks. However, recurrent neural networks do possess this capability as well. What do you mean by parameters? We have discussed what parameters previously.
Input features we have discussed, no?
Input feature
Weights and
is
bias.
feature vector. Exactly. Parameter
Weights
means weights
and
and bias.
bias.
Right, right.
Bias.
So weights are W1, W2, W3, and so on and so forth, as many number of feature vectors. And bias is the constant term associated with it. So when I discuss parameters, I'm meaning weights and bias. You know the concept of epochs? Has it been discussed?
Yes, ma'am. Once complete scan.
Yes. So every time you train your model, you are using some amount of computational time, right? So if you want you to train your model faster, there will be a certain amount of compromise associated. If you quicken or hasten your model training, that means there is a certain compromise on the efficiency or performance of your model, right? So basically, you need an optimization in terms of parameters such that your training time is reduced. Right, the rate, for example, learning rate we had discussed, right? So if learning rate is increased very fast, that means it will be able to train faster, but then it is possible that the efficiency of the model may decrease. So that is what it is. Similarly, there are other terms associated with it, which we will be discussing in the subsequent lecture. For example, you're not revising your parameter, you're using the same parameter. So will it increase your time or will it decrease your time?
Could you repeat your question, ma'am, please?
For example, if you are not going to the repeat exercise, you remember that we had discussed this formulation W mu equals to W old minus alpha times dj by dw.
Okay.
Weight updation formula.
Yes, weights. You are updating the weight. Similarly, you can also update your bias. So basically, you are updating your parameter.
Right.
So you remember that?
Yes.
Yes.
Okay. Now understand that instead of that, if you were to go for the same parameter, you use the same parameters associated with it, and you are training your model in each propagation. So will it reduce your time or will it increase your time?
Propagation time is less, na?
Yes, propagation time is less now. So
Less, then
basically,
it will improve. It will improve your training time.
it will improve your training time, right? So basically, sharing your parameters over your number of as many number of updates that you are doing, that is enhancing your training time. See these lines,
Okay.
these lines they connect. These lines are basically nothing but your weight parameter.
Think the parameters improves the performance. Do you mean to say?
Yeah. So basically, yes, it will improve the performance in terms of time, not in terms of accuracy. Accuracy is again this is something which you need to optimize. For example, here this line. What do you mean? What do you think this line signifies? This connection.
Input to the next layer, na?
This signifies the
From
weight associated with it.
weight associated. Huh?
Exactly. So that is the parameter associated with it. So if this line, this input node is connected to this hidden layer node by this line, basically this is acting as the feature vector and this is the weight associated with it. Right? So there are so many weights associated with all these input feature vectors for each of the node. And these connections are to be done with all of these nodes. For example, if I'm talking of this node will have connections with all of the 5 nodes here from the preceding layer. Similarly, this will also have a connection with all of the 5 nodes of the preceding layer, and so on and so forth. So all of these connections, they symbolize the weights associated with those connections. Okay, understand that this may be the output layer, for example. So if this is the output layer, then the output here is associated with all of these 5, and those weights values will be different from the weight values associated with this node for all the 5 inputs, right? So they will not be same,
Yes, weight
right?
values will be different.
Right. And now assume that you are training, this is the convolutional neural network. So if that is the case, then you are also not just training your weight, you're also updating with your weight values now. Right. So in each iteration, if you're updating your weight, instead of that, if you take a constant value of weight associated with that feature vector, then it is essentially reducing your time.
We are saving the time of updating the weight based on the difference between the actual
Yes,
output
you're
and the.
using the same parameter over and over,
Okay,
right?
understood. Okay, yeah, we
You're
are
using
saving
the
time.
same parameter, only you're training on that data, right? So this parameter updation time, and on that basis, on the basis of that parameter, the training time, that is remarkably reduced, right?
Yes,
That is possible in
Possible in RNN and RNN. Na?
and CNN.
No recurrent connections. What are no special relationships?
Okay. So recurrent means the word
Feedback.
recurrent actually means that it is this way.
Feedback.
Yeah,
Feedback.
this is forward. This is forward, right?
Feed forward.
Now
Huh.
understand backward. This is backward. This way is backward, right? So this thing is happening in case of RNN. Like I said, that RNN trains on the basis of previous timestamp data. So it is the training is done on the basis of sequential data. When there is a timeline associated with it, it is also training on the basis of previous data, right? Previous experience. That is not the case with ANN and CNN. The name itself actually signifies that it
We
is.
can also understand like this. No special relation means only one dimensional data. No two-dimensional data is valid for ANN.
Yes,
Only
spatial
one
relation.
dimension.
I would say that okay, in 2D, if you perceive, then
Yeah.
or maybe n-dimensional space, whatever you can perceive. For example, like I discussed that you have the number 1, You have various pictures associated with the number 1 written in various handwriting. Now you have to train your model such that it recognizes whichever way you write 1, it will recognize that this is number 1. So now those number of images that you have, is it possible that all the time you will have your number in the center only? It is possible that some images may have your number placed in the right side, somewhere it is in the top corner, somewhere it is bottom, somewhere it is center. It is possible. So there is a spatial component associated with it also. It is not just the pattern, it is also the location of the pattern, right? So in case of CNN, now when you are scanning through the grid, the entire grid of your pixels, in case of
Yes.
CNN, it is
Access.
irrespective of that. It is scanning through the whole probe. It is scanning through the whole image,
Yeah.
right? So
Yes.
when it
Yes.
is scanning in the form of, what is rastering? You understand
Yes.
rastering, right? So it is rastering through the whole image, and it is locating wherever you get a certain pattern or arrangement of pixels, right? So it is irrespective of whether it is present in the center or corner or wherever. So that is possible only in the case of CNN. But there is a special component associated with ANN and RNN. So that is why this is written that spatial relationships, it is possible in case of CNN, whereas in the other two cases it is not possible. By spatial, you understand it says space. We say no that this is the time axis, this is the space axis. You understand that, right?
Yeah.
Yeah.
Okay.
Yeah.
Okay. Can proceed, madam. Proceed.
Okay, so with this we move to the questions that were raised. Assignment 6, question number 4. Can you elaborate what this question means? What you have understood by this question?
Actually, not.
Okay, anyone who has understood this question?
Yeah. To generate the first pattern,
Mm-hmm.
which operation is to be conducted on H1 and H2,
Hmm.
whether R operation and operation or combinations thereof.
Right. So basically, you have been given an output, which is the top image. So this is the top image that has been given to you as the output. You have the vertical axis as x2, you have the horizontal axis as x1, and you have certain demarcations in this space that has been given, and in this space those demarcations have a binary component associated with it. It is +1 or it is -1. Basically binary, so you can assume it as 0 or 1, or on or off, or maybe true or false, whatever, it is binary, right? So maybe for the sake of simplicity you could assume that +1 signifies 1 or true, and -1 signifies 0 or false. So now here there are two inputs, sample inputs, that have been given to you, h1 and h2, and those demarcations are shown. And now on the basis of certain and or not all these gates, you have to choose a particular equation or logic such that you can generate this output. This is your question. So basically you have to use these two combinations and generate this is what it is. So if that is the case, then yeah, this is your output, this is your h1, and this is your h2, and correspondingly from your h1 you can make what is not h1, and from your h2 what is not h2. Is this much clear?
Okay, okay,
Yes.
like a
Yes.
puzzle sort of.
Yes.
Okay.
So if that is the case, then using these combinations, now let us scan through the options they are given. So we have basically three options here, and the fourth option is none of this. So first option says h1 and not h2. So when you say h1 and not h2, you have to use this and pass it through the AND gate and generate what is the output. So if you pass these two inputs, these two diagonal inputs through the AND gate, you get this output. Followed me so far?
Okay. Yes, ma'am.
Okay. And similarly, there is an OR gate associated with it, and there is another one that is not h1 and h2. So not h1 and h2, again there is an AND associated with it, and if you pass it through AND gate, this is what you generate. And these two are connected with an OR. So if you take this or this, if you pass these two from the OR gate, you basically generate this. Following me so far?
Right. Yes, ma'am.
Right? So other two options, if you see, H1 or not H2. So H1 and not H2. Pass it through the OR gate, you generate this. And similarly, not H1 or H2. Not H1 or H2. Pass it through the OR gate and you generate this. That will not give you this output in the AND gate. Do you follow me so far? It will be the reverse actually.
Okay.
These two will
Yes,
be
ma'am.
purple and these two will be orange, which is the opposite of it. So you're not getting it in the second case. Similarly, the third case also you can give it a try. It is H1 and H2. So H1 and H2. If you pass these two in the AND gate, you get this. And if you pass these two in the OR gate, you get this. Right? That is what it is, H1 or H2. And then these two outputs, you have to pass it through the OR gate. So if I pass this and this through the OR gate, I'm not going to get this. Followed me so far?
Got it.
Ma'am,
Yes.
how this option ABC has formed by AND or?
Forget the rest. Focus on H1 and not H2 and pass these two through the AND gate. So now your four regions that are there here, what will you color it? For example, here this lower region is purple. Here also the lower region is purple. And if you pass and in both these, +1 and +1, so true and true gives output as true. So you color this bottom one as purple. Now here this right side one, here it is purple and here it is orange. So true and false passing through AND gate will give you false. So it is orange. Similarly, the upper portion here is orange and the upper portion here is also orange, right? If you pass it through the AND gate, it is going to give you orange. So here you have orange, right? And here also the left portion, if you see, it is orange and here it is purple. So it is false and true. Pass it through the AND gate, it gives you false. So you have this orange, this orange, this orange. Only this is your purple. So we have dealt with
Got
the
it,
first
ma'am.
bracket. Similarly, you deal with the second bracket and pass these two now from the OR gate. Right? So first one, second one, and pass it through the OR gate. So effectively, what is your output? This.
Yes, ma'am. Please move on to the next question.
Okay. So with this, we move to the next question. So yes, this I have to explicitly discuss. So which is true about model capacity, where model capacity means the ability of neural network to approximate complex functions. So essentially, what do you mean by model capacity? In this diagram, if we discuss what is model capacity,
Ability to store more number of patterns.
how does that happen? In this diagram, where can you count model
The
complexity?
number of hidden layers, I think, ma'am.
Yes.
Yeah.
Number of hidden
Number of
layers.
hidden layers. If we increase number of hidden layers, model capacity will increase.
Okay, so if that is the case, so if I had, say, suppose this model, in this model I have 5 input nodes. Instead of that, just put 3 input nodes and have the same complexity of the model. So will the model capacity increase or decrease?
Yes.
Because the hidden
It will
layer
remain-
number is still same.
Model
Remain
capacity
same.
increases.
Remain same. It will not increase or decrease because input vector, feature vectors we are adding into this at the input layer.
So with this, we are also having less number of nodes in your hidden layers. Say suppose I just shun it off from here.
We got your question, ma'am. Only
Yeah.
three nodes. Let us say there are only the upper 3 layer nodes
Yes.
network available.
Yes. So now
So
your model complexity has changed. So now will your model capacity increase or decrease, or will it remain same?
Increases on
remains same.
does not depends on input.
It does
Depends
not
only
depend
on
on input. It is not the count of input which matters. It is the
it depends
connections.
on hmm.
See, when you talk of model capacity, then essentially, if you count all these connections, no, all these connections are adding to your computations, right?
Yes,
So
yes.
if
Yes.
these connections increase or decrease, your model capacity will accordingly increase or decrease.
Okay.
Input number of inputs are not going to directly affect your model capacity, but because of those number of input change, what is happening is these number of connections are changing, and these connections are essentially your computations, right?
Yes.
So basically, it is not the counts of hidden layers which is the model capacity, it is the count of these connections,
Computation. Okay.
right? So if that is model capacity, then yes, increasing the number of hidden layers will increase the model capacity. Why so?
If we increase number of hidden
Patience.
layers, computations are also increases.
Exactly. So computations will increase, your model capacity will increase, and accordingly, your time, computational time will also increase,
We
right?
can
So that
yes.
is it. Okay, what about dropout ratio? What do you understand by dropout ratio? Simplistic terms, layman terms.
The number of nodes which are not participating in these competitions.
So how do you decide that?
If there is
By
no connection between nodes.
No, you cannot dismiss a connection between the node just like that. You have to have a decisive factor associated with it.
If the weights for a particular node are not changing
Mhm.
significantly, then that node we can eliminate. That is dropping out.
Yes, not changing would be inappropriate if the weight is
Very
less.
small change. Very
Very
small
small.
change.
Yes, yes. So if the weightage is less, what happens is, it may be treated as not contributing much in the training of your
Learning
model.
process.
Yes, training
Learning
of your model.
process. Right.
So that
Yes.
may be treated as, for example, that may be treated as an outlier. In the case of outliers, this can happen, right? So such instances which are not going to contribute much to the training of your model, they can be eliminated, so that this redundant time taken to train the model on the basis of those particular nodes, that is shunned off, because that is not going to matter much. So we decide dropout ratio. Ideally it is maybe 30% or 20%, whatever, like, it depends on your data again and your model. But yeah, so if you use this kind of ratio, so that many fraction of unusable or less usable node or connections, they can be eliminated. So if, for example, amongst five, if I have to choose, say, 20%, so what is 20% of 5? It's 1, right?
Yes, yes.
Yeah, so amongst 5, if I eliminate 1, so I'm left with 4. So have I changed the number of connections?
Yes.
How many? Is it
Yes.
Definitely.
increasing or decreasing?
Decreases.
Connections
It
are
is decreasing.
decreasing.
It is decreasing means model capacity is
Decreases.
decreasing. Okay, so if I increase my dropout ratio from 20%, I make it 40%. So instead of 4, now I have 3 usable
Capacity
nodes. So model
Model
capacity
capacity
is,
decreases
decreases.
further.
it decreases further. Exactly. So is B correct?
No, no, no.
Not.
No.
You understand dropout ratio now?
Yes.
Yes, yes.
It is inversely related to each other. No?
Exactly.
Yeah.
And what about learning rate? Do you understand learning rate? I think we've covered it in the previous classes.
Learning rate is
Amount
constant.
of amount
The
of step that we take in gradient descent.
Hmm. So how does it affect model capacity?
And I think it
Actually,
decreases the capacity.
Why do you
no,
say that?
learning rate is mainly affecting the optimum weight.
Hmm.
It has nothing to do with the model capacity.
Exactly, exactly. It is not going to create any difference on the model
because we
capacity.
consider it as a constant, no?
Not really constant. It may vary, but it is not going to change your model capacity, because essentially those number
Right.
of computations you still need to do, right? Your
Okay.
optimization of weights, the parameters associated with it, you are maybe updating faster, but the training process, it has to go through all these, right? These connections are not going to change. Will
Okay.
it change? If I change, for example, this weight value from, say, suppose 0.2 to I change it to 0.3, so will it change that number of this connection? Will it vanish this connection?
No, it does not vanish the connection.
Does it add the connection?
No, it does not
It
add
does
any
not
another
add either,
connection.
right? So if I update my learning rate, my rate of change of those parameters will change, but it is not going to affect my model capacity.
Okay.
Followed me so far?
Yes, yes.
Yes,
Okay.
ma'am.
So now that you have understood what is model capacity, dropout ratio, learning rate, so we will move on to, yeah, this question. So how many of you have attempted this question?
I have a doubt now. I can't
Yes.
understand the question.
See, we have discussed gradient descent. So by gradient descent, you understand that you choose any arbitrary point and you go to the minimum value of the parameter
Yes.
in the steepest direction associated with that curve. For example, this is the
Okay.
3D graph. So here, if I have a point somewhere here, the steepest direction is this way. So I'm not going to wander about here and here or here. I'm going to descend downwards in the steepest gradient direction, and I will
Okay.
finally land in the minima position. So now here the question says first order gradient descent would not work correctly or may get stuck in which of the following graphs. So essentially we also discussed that any of the curves, any order curve that we have to have a global minima in order to have this gradient descent to work. If we have multiple global minima, then it is not going to work,
Okay.
right? So if that is the concept, then here do we have just one global minima?
No.
So
I,
now where can I get stuck? For example, this point, I've just blown this image up. Okay, so this point. Now, when we talk of gradient descent, we are basically dealing with your cost function. Okay, and that cost function essentially we are trying to minimize by taking a derivative with respect to all the parameters associated with it. For example, suppose that this is 3D. So this is your j. This vertical axis is your j cost function, and this planar axis here is suppose your y and this is your x. Okay, so this is my
Okay.
x and this is my y. I have okay, so for simplicity don't take it xy, you will confuse again. Just take it as uh, x1 and x2. This will be better, or maybe w1 and w2. So these are weights. Okay, these are the parameters that you are updating, and this vertical axis is your cost function. Okay, so if that is the case, then I am saying that this is my x-axis, w1 axis. So with respect to w1 axis, if I plot, then I see that the curve is something like this. On this plane, this at this point, the curve is something like this. Because where am I looking? This w1 axis. So in my
Yes.
w1 axis, this is something like this. So this point acts as the minima or maxima.
Minimum.
How is it minima? The curve is
And
something like this.
we are going upward, it is maximum.
It is maxima, right?
Yeah.
Yes.
Okay.
You can picture it, right? It is something like this.
Okay.
Yes,
So
yes.
this is maxima. Okay, now look it from this perspective here.
And no, in W2 perspective.
Yes, in
Not
W2
W.
perspective. So now your
Mm.
axis is this one. This W2 equal to 0 here. This is your axis. So here your graph is like this. So this point is minima or maximum?
Minima.
Minima. So basically, if you have a function, say suppose x square minus y square, if this is your function of your cost function, suppose j is this, and x is your w1 and y is your w2. So if you take the first derivative with respect to x, then it is 2x, and if you
Yes.
equate x to 0, then basically derivative is 0 here. If you take single derivative df by dx with respect to x, you have differentiated this function, the partial derivative with respect to x, you get 2x. And
Two.
the gradient, if you take the value of x as 0, so at 0 this point, you get df by dx equal to 0. So this means that it is either a point of inflection or a point of minima or a point of maximum. That is what this means, right?
Yes, yes.
So now we take a double derivative here, d2f by dx square, and you get plus 2. So it is a minima or a maximum?
Minimum.
It is a minimum. Okay, now come to derivative with respect to y. So the same function, you are taking a partial derivative with respect to y. Now it is minus 2y. So if you equate y to 0, then it is 0. That means again it is either a point of maxima or a point of minima or a point of inflection. Now I take the double derivative. What is the double derivative with respect to y? Minus 2. Now it is minima or maxima?
Maximum.
It is maxima. So basically you are stuck at a point which is neither a minima nor a maxima of this function, and every time you try to optimize it, it will keep on holding it back at this position. It is a kind of loop. For example, if I just picture it this way, yeah, 2D is easier to understand. So this 2D diagram, I want you to associate with this 3D picture. So when I talk in terms of x, you are to picture it this way, and when I talk in terms of y, you are to picture it this way. So accordingly, we will discuss this 2D graph. So what I am saying is, so every time you come here and you try to update your x, it takes you here and here. It rotates or oscillates about this point only. It is stuck here. It is not going to give you an exact global minima value. It is not going to leave that value. So essentially, you can see figuratively that you have to come somewhere here in order to reach your minima value. But if you are oscillating about this value only somewhere, then you will never be able to escape this region, because every time you increase your weight, it will update your new weight such that this will become positive. And now the moment you go here in the positive direction, it will update it such a way that it becomes negative, and you keep on swinging here only. You are not able to move out from here so that you can go somewhere else. It is in 2D, you are able to see that the curve is like this in this case, from this perspective. The moment you're talking of y, then the curve is like this, inverted. So you have to leave this point and you have to go navigate to the global minima value. So if you are stuck here, if you are not able to update every time, your iterations are such that every time you are, once you are adding, the next time you are subtracting. So basically you are oscillating about this point. So this point is called the saddle point. You understand the limitation of this, why this is happening?
Yes, ma'am. Like from one axis we are getting maximum, we are other it is giving the same as minimum.
Right. So it is not the functional minimum value. This j function minima is somewhere here or maybe that side. It is somewhere here. It is not close to that point, but you are navigating around that point only. Every time you try to update it in the subsequent iterations, you are just moving to and fro. That's all you're doing. So you have to come out of this loops. You have to take a jump from that value such that now the steepest direction will change. So from here, instead of taking a small increment with respect to our learning rate, if we add an incremental value, a large incremental value, and moves outside of that loop, then yes, then I will be able to update further such that I go to the global minimum. So for that, what they do is, if this happens during the training of your model, if this loop happens, then you simply take alpha times bracket, within bracket you have dj by dw plus maybe 10 or 20 or maybe whatever, like some larger value in your range, of course. So that will basically navigate out of this loop. Now, somewhere here or here or here, anywhere, you're not going back there. You're going to go to the steepest direction such that you land to the global minimum. So this loop where you're basically stuck, this is called as the saddle point. This is an ideal example of saddle point problem. That is why this is not suitable for gradient descent. This kind of function is not suitable for gradient descent problems. You understand what is the issue with this, right?
Yes, ma'am.
Okay, so any more doubts here?
No, which answer is correct?
So
A.
The question
B.
says in which of the following
Would
graphs
not.
it will not
Would
work
not.
correctly. So when it is not work correctly, the answer is B.
B. B.
Okay, right. Thank you.
Please move on to the next question now.
No.
Can
It's
you also
same
read the
assignment
question
we are
3?
having question 3.
Question 3.
Yeah.
So I will just go to the assignment
Same.
of the same assignment.
Yes, same assignment.
Yes.
Question number 3.
Oh, week 6. Just a minute. Yes, please. This is your question.
Yes.
Very
Yes.
simple question.
So what is your doubt here?
How we have to calculate these points?
Ma'am, like here it is x q equals to x plus y, and f as if it's a function of q star z. So we take -2, 5, and 4 as weights, right?
Right.
So I mean, and how do we, I mean, compute the results over here? Like we are not having input values, we are having weights. What I remember is that we multiply weight with the input values and then we proceed further, right?
Yeah, so it has a summation term which is associated with your this value and the weights associated with it.
So if we can just calculate the first one, like -2 and 5 from x and y, if we just need to sum it, like it will be +3.
Yes,
Okay.
this relation, this is showing you the relation, what this neuron signifies.
Okay.
So essentially this is shown to you, and in fact it is written also here.
Yeah. So it is -2 plus 5, that is with the help of the relation that we have, +3. Then 3 into 3 and
Star
the,
means here, star means into, and it is shown here.
yeah.
So
So
basically this, the output from x and y is q, and that output is an input for this neuron, and there is another input z from that neuron, from this layer, and these two basically have this relation. So if you multiply 3 with -4, it is giving you -12. So this example has been shown to you.
Okay, same we have to apply the next points also for A like that. Or
So
how
when
we
you say
calculate
gradient, what do you understand by gradient?
Derivative.
Yes, it is
Derivative.
derivative.
First
It is
you make
derivative.
the expression for f is equal to q into z. Q is given as x plus y. So x
Exactly.
plus y into z, which is equal to xz plus yz. Now you derivate with respect to x, with respect to y, with respect to z.
Okay.
X, y, z values are already given as -2, 5, -4.
Okay.
So you derivate that df by dx is equal to what you get? Xz plus yz. Yz becomes 0. Xz will become z. So df by dx will be equal to z. Z means -4. Next derivate with y. df by dy is equal to xz plus yz. So xz will become 0 because there is no y term. So
And
yz
each and
derivative
every
term you have to derivate.
sir,
First, completely write the expression for f. Then you derivate with
So,
x, derivate with y,
Z,
derivate with
Y,
z.
Z.
That's all.
Okay.
You get the answer.
Don't look at this diagram only. This is just for your simplistic understanding so that you can relate these two equations pictorially. Just forget it for now. If that is creating a doubt, then just forget it for now. Just deal with these two equations mathematically. So if you deal with it mathematically, you have an expression of q, and that q has been used in your second equation, isn't it?
Yes.
So you can substitute your q now.
Yeah, F will get xz plus yz.
Yes. So if you have your f now in terms of x and y and z, so now it is possible to take a partial derivative with respect to these three, right? Or not?
Yes. Yes, that's how we will take the partial derivatives. That is my doubt. Dou f by dou x equal to, if we derivate the equation with respect to of x, we will get z only.
Yes, you
Yes,
have.
Z value is -4. So
That
the
is
first
given
one
to you,
will be
right?
yeah, -4 is
Z
given.
value is -4. Yes.
So that
So
is your
okay,
value.
okay. So it is also -4. Next we will take dou f by dou y. Again we get z, that is -4. And if we take instead of in respect to of z, we will get y. Now y value equal to 5.
No. You will get x plus y.
X plus y, no?
Plus y.
Ah,
With
yeah, yeah,
respect to
yeah,
z, you
yeah,
have
yeah,
two
yeah.
terms.
Ah, yeah. X plus 5, that is -2 plus 5, we will get 3. So the answer is -4, 3. Is it right?
Exactly. Yes, he is your answer.
Yeah. Okay, thank you.
So just to understand, like we get the final equation as f equals to xz plus yz.
Yes.
We make derivative with respect to df by dx, df by dy, and df by dz. So derivative will be like z plus yz, right? For by when we do with x.
No, when you are talking of partial derivatives, then you are assuming that the other parameters are taken as constant.
Okay.
So when you assume it
When
as
we
constant,
are
then the
doing
first
with
derivative
respect
of
to
the
x,
constant will be taken as 0, unless that
0.
constant is proceeding as a multiplication for your given differentiator. For example, if you are taking derivative with respect to x, then any term which has x associated with it, or any power of x associated with it, so that constant will be taken as a coefficient. Other than that, any other value which is not having x or x power something, then that
Okay.
is taken as a constant.
When we are taking derivative with respect to s, we have to take other terms like y
And
and
z
z are
as
constant.
constant. That is what partial
As
derivative
constants.
means. Yes.
So for constant, the partial derivative is 0.
Yes, of course. For
That so
constant, the
it,
derivative is 0. Since you are
the
using partial
constant of
derivatives,
derivative
you
is
are
0.
treating others as constant.
Yes.
So, for example, assume that it is not a term. Assume that you have x plus 2, and you differentiate x plus 2 with respect to x. Then what is your answer?
X plus 2 with respect 1.
1. What about 2? Differentiating 2 with respect to x, what is it?
0.
0.
0.
So why? Because 2 is a constant, right?
Constant.
So when
Yes.
you are taking a partial derivative with respect to x, then you're treating any terms associated solely with y and z as constant. So your first term here is xz and second term is yz. So when you are differentiating with respect to xz, then your first term has a coefficient of x, right? Where z is
Yeah.
your constant and x is the variable that you are
Yes.
differentiating it with respect to.
Yes.
The second term yz has no component of x. So you can treat yz as constant. The product of yz is a constant for
Okay.
that particular instance.
Okay.
Now, the moment you are differentiating with respect to y, this consideration vanishes. Now you have to treat xz as constant, and yz will be the term that you will be actually differentiating.
Okay. Okay, understood. And that's why in the last one, since Z was there in
Both
both,
the cases, yes.
so we considered both of them. We do not make it zero. I mean, constant.
Yes, of course.
Understood. Okay. Thank you. Thank you.
And this is not associated to actually machine learning. This is like, I think this is basic calculus.
Yeah.
Yeah.
Thank you, ma'am.
Okay.
Thank you very much.
Okay.
Thank you very much.
Chalo. Thank you.